You know, there's a specific frustration I think everyone has felt with modern technology.
Oh, yeah.
You have a computer in your pocket that can simulate a nuclear explosion. It can render a 3D open world in real time. It can absolutely destroy a grandmaster at chess.
Right.
But if you try to have a genuine conversation with it, and I don't mean asking Siri for the weather, I mean a conversation with a bit of wit or, a tiny bit of social nuance.
It just falls apart.
It feels like talking to a very smart, very literal alien.
It really is the central paradox of artificial intelligence. We cracked high-level calculus and logic decades ago. But basic conversation, the stuff a 4-year-old does effortlessly while playing with blocks, that is still the frontier.
And that is the gap we're trying to bridge today. We're looking at a stack of research on linguistic modeling. And I want to be clear, this isn't just about how chatbots work. It's about the fundamental theory of how you map the messy biological reality of human thought onto the cold, rigid logic of binary code.
Right. And the sources we have today are fascinating because they don't just look at the code, they look at the philosophy behind it. They ask, if we want a machine to speak, do we need to build an artificial brain? Or do we just need to fake it well enough that nobody notices the difference?
So let's start with that word, modeling.
Yeah.
Because in my head, a model is, a miniature train set. It looks like the real thing. It has little wheels and tracks, just smaller.
Right.
Is that how linguistics uses the term?
Not quite, and the distinction is crucial for everything we're going to discuss.
Yeah.
In the natural sciences, we say system A, model system B, if they behave similarly.
Okay.
But, and this is the key from our research system, A does not have to be physically constructed like system B.
Okay, give me a concrete example.
Think of a chemical reaction like an explosion. You can model that explosion using mathematical equations on a chalkboard.
Right.
The equations aren't made of gunpowder. They don't get hot. They don't make a noise. But the output of the equation matches the output of the explosion.
So for linguistics, we don't need the computer to literally have what? Squishy neurons inside a skull.
No.
We just needed to take an input, a sentence, and produce an output that looks like something a human would say.
Precisely. We're looking for functional equivalence, not structural identity. We want the math to match the result, even if the machinery is totally different.
But here's where I get stuck, and I think this is the first logical stop on our roadmap. If we have the blueprint for language right inside our heads, literally the human brain, why don't we just copy the structural identity?
It seems like the obvious path.
Why not just reverse engineer the brain?
You're referring to the neurolinguistic model. It's the obvious first step, right? We know language comes from electrical and chemical signals in the brain, so let's map the nerves.
Build a digital brain, get digital speech.
It seems like the most direct path. We map the hardware, we get the software.
So what's the problem?
The problem is the Heisenberg nature of the toolset. The source material points out that the brain has billions of neurons, and each one connects to hundreds of others via dendrites and axons.
And these are microscopic.
Microscopic. To observe them functioning in real time, you have to intrude.
And by intruding, you break the machine.
Or at least you alter the activity you're trying to measure.
Yeah.
You can't just open the hood and watch the combustion engine run while you're driving down the highway at 60 miles an hour.
On the scale.
The scale is simply impossible. The text calls it a grandiose multiplicity of causal chains.
Which is a very fancy way of saying it's too complicated.
It's a storm. We aren't talking about a single wire lighting up for the word apple. We're talking about a storm of activity across vast regions of the brain, all happening simultaneously.
So the number of variables is just too high for us to model computationally.
Currently, yes. It's a dead end for a complete linguistic model.
Wait, I have to push back on that slightly. We hear about neural networks in AI constantly. ChatGPT, Gemini, Claude, they all claim to be neural networks.
They do.
Isn't that modeling the brain?
It's a great marketing term, but it is a bit of a misnomer. The research makes a sharp distinction here. Computer science uses formal neurons.
Formal neurons.
These are simplified, logical, units math gates that we invented.
So they're inspired by the brain, but they aren't the brain.
Exactly. They model our invention, not the biological reality. A digital neural network finds statistical patterns in data. It doesn't trace the biological pathway of thought. It's like drawing a map of the subway system that ignores the tunnels and just connects the stations with straight lines. It works for navigation.
But it doesn't tell you how the trains actually run.
Exactly.
Okay, so the biological route is a no-go. We can't look at the hardware because it's too complex and we can't touch it without breaking it. So what about the software?
The behavior.
If we can't look at the nerves, can't we just observe the behavior?
This brings us to the psychological approach. Psycholinguistic models. This is essentially the stimulus-response method.
Like Pavlov and his dogs.
Similar idea. You treat the speaker as a black box subject, but you focus on their behavior. I give you a stimulus, say the word Rosa.
And you record my response.
And I record your response. Maybe you say Roja or flower or parks.
Or I say Diaz.
Right? Or I give you a confusing sentence and I stopwatch exactly how long it takes you to figure it out.
And what does that data build?
It builds a profile of you. It's fantastic for identifying personality types or diagnosing cognitive delays or understanding social behavior. But here's the catch.
What's the catch?
Does it explain how language works? No.
It tells you what the driver is doing, but it doesn't tell you how the car works.
Exactly. The source notes that psycholinguistics usually borrows concepts from linguistics to explain psychology. It doesn't go the other way around. It doesn't offer a holistic set of rules to teach a computer to speak.
It's just observing the output.
It observes the output, but it doesn't give us the code to generate it.
So we've hit two walls. We can't copy the biology. It's too complex. We can't rely on psychology. It's too focused on the user, not the system.
We need a third option.
And this is where the story pivots to the functional model. We go back to that term black box, but in a different way.
Right. This is the cybernetic approach.
The functional model.
This is the paradigm that actually drives most of the utility we have today. The concept is, I don't care what happens inside the box. I only care that the input matches the output.
So we treat language strictly as a device.
A conversion device. We imagine an analyzing box that takes text and converts it into a representation of meaning.
And then the reverse.
And a synthesizing box that takes meaning and converts it back into text. The goal is to strip away all the anthropomorphic features.
Meaning we stop pretending the computer has feelings or neurons or a childhood.
Correct. We only care about the rules of conversion. And for this to work, the model needs to be two things: dynamic and formal.
Define formal in this context, because usually that means wearing a tie.
In logic, formal means rigorous and explicit. It can't rely on, you know what I mean? It has to be a set of mathematical or logical instructions that an automaton can execute without a human standing over its shoulder.
And dynamic.
It means it's not a static dictionary. It isn't just a list of cat equals gatto. It's a process.
It's a set of rules.
A set of rules for handling data. This leads to the most important principle in modern software engineering: independence. The algorithms, the code, are separate from the data, the language rules.
Which makes sense. If I want to teach my program Spanish instead of English, I shouldn't have to rewrite the entire engine.
You shouldn't.
I should just be able to swap out the data cartridge.
Exactly. The machine is the same, the fuel changes.
So let's look at one of these functional models in action. The text highlights something called the meaning text theory, or MPT. It sounds almost too simple. Translating meaning into text and text back into meaning.
It sounds simple, but the execution is incredibly sophisticated. The MTT is successful because it's multi-level. It acknowledges that you can't just jump from a thought to a sentence in one leap. It proposes a pipeline.
Walk us through the pipeline.
You start with semantics, the raw meaning, this web of ideas. Then you move to deep syntax, the abstract structure.
Okay.
Then surface syntax, the actual grammar and word order. Then morphology, the shape of the words, like adding ed for past tense. And finally, you get phonetics or text.
It really is an assembly line. You start with raw steel and end up with a car.
It is, but here's the technical detail that sets MTT apart, and it's why it works for global languages. It rejects constituency in favor of dependency.
Okay, I want to dig into this because the diagrams in the notes were distinct. What is constituency?
Constituency is how we traditionally teach English in grade school. We group words by their position. The quick brown fox is a noun phrase.
Right.
It sits next to the verb phrase. It relies heavily on word order. Imagine beads on a string. If you cut the string, the beads fall off. The order is lost.
Because in English, order is meaning. Dog bites man is a news story. Man bites dog is something else.
Right, but that bead on a string model falls apart in languages like Russian or Latin or even Spanish. In those languages, you can often scramble the word order, and the sentence still makes sense.
Because the words have endings that link them.
Exactly. So if you build a model based on English word order on constituency, it chokes on Russian.
So what's the alternative?
MTT uses dependency trees. Don't think of beads on a string. Think of a molecule. You have a central atom, the verb, And other atoms, the subject, the object, are chemically bonded to it.
They orbit the verb.
They orbit the verb. And because they're bonded, you can rotate the molecule and the structure stays the same.
That makes sense. The subject is still the subject, whether it comes before or after the verb.
Exactly. By focusing on the links between words rather than their linear position, the model becomes universally applicable.
That is a much more flexible architecture. Now, within this model, there's a concept I found absolutely fascinating called lexical functions.
Yeah.
To me, this explains the uncanny valley of AI speech. You know, when a computer helps you with grammar but still sounds off.
Yes. This addresses the problem of collocation. These are words that belong together not because of pure logic, but because of custom.
The example in the notes was heart attack.
Right. You have a medical event involving the heart. In English, we call that an attack.
But we also use the word cordial. Cordial greetings.
Yeah.
And cordial etymologically means of the heart.
But if you walked into an emergency room and said, "Help, my father is having a hearty attack," or "he's having a cardiac occurrence,"
Yes, people would look at you funny.
they might understand you, but you sound alien. You sound like a robot, even though logically, hearty and cordial and cardiac map to the same semantic concept.
Right.
A purely logical model would say those are interchangeable. A functional model uses lexical functions to say, stop. If the concept is medical failure and the organ is heart, the only allowed verb is attack.
So it creates these rigid equations for naturalness?
And it allows for something else. Paraphrasing. This is huge for chatbots.
Oh, absolutely. If a computer only has one way to say something, it gets repetitive fast.
I do not understand. I do not understand.
Exactly.
Right. But the model can formally prove that the Spanish sentence, Juan me prestó ayuda, Juan lent me help, is mathematically equivalent to Juan me ayudó. Juan helped me.
So the system can vary its output to sound more human while keeping the semantic meaning identical.
It creates variety without losing accuracy. That's the holy grail.
Okay, but what happens when the data runs out? We're constantly inventing new words, slang, tech terms. If the model is just a set of rules, doesn't it break when I say something that isn't in its dictionary?
This is where we get into analogy. A smart model doesn't just look up words, it looks at patterns. The text gives a great historical example involving Spanish pronunciation.
The spi to esp rule.
Correct. In Latin, you had many words starting with esp or sint, specialis, spectaculum, statua. But as Spanish evolved, speakers found that initial S cluster difficult to pronounce. So unconsciously, they applied a rule. Add an E to the front.
Specigere spectaculo estatua.
Now, fast forward 1,000 years. We introduce English words to Spanish. Standard, scanner, slogan.
And they become a standard, a scanner, a slogan.
The speakers apply the ancient rule to the new data by analogy. A functional model can be programmed to do the same. It can predict how a new word should behave.
The best example of this was the made-up tech words. The texts use the example internetizar.
Internetizar. Now, if a computer sees this, it might panic. It's not in the dictionary. But if it has a morphological analyzer, remember, looking at the shape of the word,
It breaks it down.
it breaks it down. It sees internet. It sees the suffix izar.
Which acts like indicize in English, to make something function.
So the computer deduces. Internetizar means to make something function on the principles of the internet.
But the text took it a step further with Linuxar. Let's say the computer has no idea what Linux is. It's a variable X.
The analogy still holds. It knows izar. So it creates a structural comprehension to make something function like unknown variable X.
So it can handle the grammar of the sentence perfectly, even without knowing what the noun means.
That is the power of a functional model. It can guess based on structure.
So we have these complex, full-blown models like MTT that can handle dependency trees and deep syntax. But the source material makes a practical point. We don't always need the Ferrari engine to go to the grocery store.
Correct. These are called reduced models. You don't need a full linguistic breakdown for every application.
Give me a use case where we'd strip the engine down.
Google search. When you type a search query, do you care if the grammar is perfect?
No, I just want results.
And as a search engine, if you search for Mexican food, I want to show you results for Mexico and Mexicana too. I don't care about the grammar. I care about the stem.
The root of the word.
So I use a reduced model that chops off the endings and just matches the root. Mexican.
So ignoring the grammar actually makes the tool better.
For that specific task, yes. A spell checker is another example. It needs morphology. It needs to know that run becomes running and not running, but it doesn't really care about the meaning of the sentence.
It just checks the word forms, not the intent.
Right. Whereas a translation app
Needs the full stack.
needs the full stack.
Yeah.
Semantic, syntactic, morphological, especially if you're translating between distant languages like English and Japanese. If you use a reduced model there, you get gibberish.
This discussion highlights a bit of a philosophical battle in the field, doesn't it? The text refers to the rationalists versus the empiricists.
It is the classic conflict in linguistics. The rationalist approach, like the meaning text theory we discussed, relies on intuition, logic, and handcrafted rules.
It says, language has a structure, let's describe it.
Exactly. And the empiricists, they rely on big data, statistics. This is the dominant force in AI right now.
I don't care about the rules, just show me a billion examples and I'll find the average.
Exactly. When this phrase appears in English, this phrase usually appears in Spanish 99% of the time. It's incredibly effective.
But
the text makes a critical warning here. Empirical methods are blind without rationalist definitions.
how so? If the data is big enough, why do we need the rules?
Because you have to define what equivalent means before you can count the equivalence. You need a framework to organize the data. If you just have a billion sentences with no structure, you just have noise.
You need the rationalist logic to build the box that the empirical data lives in.
You need both.
So we have the black box, we have the rules, we have the big data. Why are we still frustrated? Why did I say at the beginning that talking to a computer feels like talking to an alien? What is the missing piece?
The source material identifies two major hurdles that even the best functional models haven't cleared: pragmatics and world knowledge.
Let's take pragmatics. That sounds like something we should have solved.
Pragmatics is understanding the intent behind the words, not just the definition. The classic example. I turn to you at dinner and ask, "Can you pass the salt?"
I pick up the salt and hand it to you.
Because you understand social convention. You understand that I'm making a request. But a computer, looking at that purely logically, sees a yes-no question about your physical capability.
Are you physically able to move the salt?
Right. And the computer says, yes, and sits there.
Technically correct.
Technically, it answered the question correctly. Pragmatically, it failed completely. It missed the invisible layer of social contract.
And the second hurdle, world knowledge. It seems like it would be easier with the internet.
You would think so, but it's the hardest problem of all. The text uses a deceptively simple sentence. Children are children.
Logically, that's a tautology. A equals A. It contains zero information.
To a computer, it's a waste of bandwidth. It's like saying 5 equals 5. But to a human, children are children is loaded with meaning.
Of course.
It implies that children are immature, energetic, playful, and crucially, that we should forgive their mistakes because of their age.
To understand those three words, you need to understand parenting, biological development, social forgiveness, everything.
You need an encyclopedia of life. You need to know how the world functions, not just how grammar functions.
And that encyclopedia is just too big to code.
Currently, yes. We can model the grammar perfectly. We can model the syntax. But modeling the entire context of the human experience, that's the missing link.
So to wrap this up, we've moved from the biological approach, which was too messy, to the psychological approach, which was too subjective and landed on the functional model.
We learned to treat language as a mechanism. By separating the analyzing from the synthesizing and using tools like dependency trees and analogy, we can get computers to handle incredible complexity.
But they're still trapped in the A equals A logic.
They are. The source leaves us with a provocative thought. We're still waiting for a new Chomsky. We have solved the structure of language, but we haven't solved the semantics of life.
That's a great way to put it.
Computers can process text, but they don't yet understand intent in the way we do. They lack the soul of the conversation.
It really makes you appreciate the software running between your own ears. The next time you hear a new slang term and instantly understand it, or the next time you understand a joke without having it explained, take a second to realize what just happened.
Yeah.
You just ran a model more complex than the most powerful supercomputer on Earth.
It really is the ultimate black box.
Thanks for listening to The Deep Dive. Catch you next time.